We're unwrapping Mars now on BBC One with Patrick Moore.
Good evening. For this programme, Mars, the red planet. Believe me, there's a lot to talk about. That's why we have a special extended programme. But first of all, we've got one news note. We've had a great comet, Comet McNaught. Not well seen from here, sadly, although Pete Lawrence did get one nice picture from Chelsea. In the southern hemisphere, it must have been really splendid, as you can see from these photographs. A really brilliant comet, the best for many years, but it will come back into our sky, but by then I fear it will have faded down below naked eye visibility. So goodbye, Comet McNaught. It won't be back for a long time, if at all. And now, Mars. We'll be getting the latest news about Mars Express. Chris had been out in America, talking about the latest NASA probes and Project Phoenix. But first, some basic Mars facts. What is Mars like? Well, it's smaller than the Earth, only just over 4,000 miles across, and further away from the Sun, about 141.5 million miles, and its year is longer than ours, 687 Earth days. On the Martian day is about 40 minutes longer than ours. Telescopes show the white polar ice cap, the red deserts, and the dark markings, once thought to be seas, and then areas of vegetation. Then now, of course, we know that they're not. Can there be life there? Well, who knows? We thought there was. Our views have changed, so let's look back now at a sky at night I presented way back in 1969.
We've just had some amazing photographs sent back by the American probe to Mars, Mariner 6. Mariner 7, by the way, has been brought back under control, and we await news from that. But meanwhile, we have this superb series of close-ups from Mariner 6, and I'd like to show you those pictures now, beginning with Mars, as seen by Mariner, from a distance of more than 700,000 miles, which, of course, is a great deal further than the Moon is from the Earth. And even so, you can see there some of the dark areas, which may be vegetation, and at the bottom you can see the white polar cap, which has always been thought to be due to some kind of icy or frosty deposit.
Well, we now know those dark areas are not vegetation, but we are finding out more all the time. And 3 years ago, NASA dispatched 2 probes, Spirit and Opportunity, to land on the surface and then rove around, examining Mars, actually from the planet itself.
Our entire view of Mars has been changed by Spirit and Opportunity, and I've enjoyed following their progress from the earliest days of testing. Their design was revolutionary, with 6-wheel drive and a fleet of scientific instruments on board. We think that billions of years ago, Mars was once a wet world, but today, that water has disappeared from the surface. Spirit and Opportunity were designed to be roving geologists, searching for evidence for this ancient water preserved in the rocks. The rovers were designed to analyse these rocks and confirm they were indeed influenced by water. Their original mission was designed to last just 90 days, but 3 years on, the rovers are still going strong. Together, they've travelled over 10 miles and sent back more than 170,000 images. Their designer, Steve Squires, was recently in the UK, and I started by asking him what made the rovers so special.
I think what we've been able to do with these rovers is to really characterize in detail for the first time what it was like to be at 2 places on the surface of Mars 3-4 billion years ago. We've known for a long time that there was probably once water on the surface. We've known for a long time that it was probably warmer in the past. But now we know a lot of details about what it would have been like to stand there, what was the chemistry of the water, what were the conditions at the surface, how suitable would it have been for life. We've really been able to piece together a lot of details about these 2 locations. Now there's a whole lot more of Mars yet to get to, but for these 2 places, we're starting to feel like we kind of understand them.
In the same way that a geologist standing on the planet would understand.
It is geology. We are on the planet. Yeah, exactly.
5, 4, 3, 2, 1, engine start. and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
And there's jettison, solid motor jettison.
Following launch in 2003, getting the two plucky rovers, Spirit and Opportunity, to Mars required resourcefulness, ingenuity and luck. Building two rovers was a form of insurance and, of course, the chance for double the science.
Currently at an altitude of 39,000 feet, moving at a velocity of 12,019 miles.
After their 6-month journey to Mars, the rovers faced the most dangerous part of any mission, the descent to the surface.
One tone. Shield. Parachute deploy has been detected. Have positive indication of parachute deploy. On the LTP.
Opportunity landed in an upland plain called Meridiani. Spirit landed in Gusev Crater, once thought to be an ancient lake and an ideal place to test for evidence of water. The first images from Spirit looked good, but proved to be an enormous disappointment.
We looked around, saw a nice flat plateau, lots of rocks. That was all good. But very quickly after we climbed down off of the lander and started looking at the rocks, we realized that they weren't sedimentary rocks at all. Mars had faked this out. The rocks were lava. I mean, it was basaltic lava, the kind of stuff you'd find in a place like Iceland or Hawaii. I'm still convinced that those layered rocks are there someplace. You know, down below us someplace, those rocks are there. But the problem is that if there was a lake there, it was 3 or 4 billion years ago, and a lot can happen. And then we got the first pictures down from Opportunity. They were just crazy looking. There was this dark soil, no rocks or boulders anywhere. And then we looked off in the distance, and there was this outcrop of layered bedrock right in front of the rover. Now, we had no idea how far away it was. It later turned out it was about 7 meters. I mean, we were right in front of it. What had happened, and it took us a few hours to realize this. The lander, which is, of course, encased in these airbags when it lands and it's bouncing and rolling, it had rolled into this little crater, like a golf ball going into the cup, right? The crater was only 20 meters in diameter, and there we were, right in the middle of it, and all around us is this just spectacular outcrop of layered bedrock. It was bizarre.
So why are outcrops so important?
Well, the thing about bedrock is that it has a comprehensible geologic pedigree, okay? If you're out driving around in a rover on Mars and you find a loose rock sitting on the surface, you don't know where it came from, okay? There are plenty of processes that can move rocks around. We have found rocks at the Spirit site, for example, that are clearly hundreds of meters, maybe kilometers away from wherever they were first born. We've found meteorites, you know, that fell from space and are sitting on the surface. And so it's very hard when you have a piece of loose rock to place it into context. Whereas when you find bedrock, that's where that rock grew up, that's where it was born, okay? And you can place it into a context and you can relate it to the other rocks around it. So finding bedrock was very important to us.
So what sort of things could Opportunity do presented with this opportunity? How do you study the rock?
Rover has many tools on it. The rover has cameras, of course, and they take those beautiful color pictures that you see. But the rover's got a lot of other capabilities as well. It's got an infrared spectrometer for looking off in the distance and seeing what rocks are made of. It's got this wonderful arm that's got a microscope on it, 2 more spectrometers to tell us in a lot of detail what the rocks are made of. It's got this tool called the RAT, the rock abrasion tool, which can grind into the rocks. And it gradually revealed its clues to us.
So what did that puzzle say?
What the puzzle said was that the rock is made largely of sulfate salts. That was a big surprise. It's very finely layered. It's a sandstone. It's a sandstone, and the individual grains of sand are very rich in sulfates. And then it's shot through with these little hard, round, spherical nodules that are made mostly of hematite.
Are these the blueberries?
These are the things we call blueberries because they're like blueberries in a muffin, yeah. And these, it turns out, are what geologists call concretions. These are things that have precipitated from liquid water that once saturated the rocks. And then also, in the layering in the rocks, we saw places where there were very fine-scale ripples that were preserved where water had flowed over the surface long ago.
Like the bottom of a riverbed?
Yeah, like what you would see when water flows over sand. And we could see that preserved in the rocks as well. So what we found here was evidence that there had been abundant water beneath the surface, and at least for limited periods of time, water actually flowing across the surface.
So what does it mean that you have sulfates rather than carbonates?
Well, part of the reason a lot of us expected carbonates is because there's always been this idea, for decades, that in the past Mars had a warmer climate because it had a denser atmosphere of carbon dioxide. Maybe that's correct, maybe it's not, but that's been a prevalent theory for a long time. If that's the case, where did the carbon dioxide go? Well, if you ask yourself, where did a lot of the carbon dioxide that's historically been in the Earth's atmosphere go, the answer is carbonate rocks. There are limestones all over the planet, and that's where a lot of the Earth's original endowment of CO2 went. So we sort of expected that might be the case on Mars. And when we got there, what we found instead was that the place is full of sulfates, and there's very little evidence for carbonates at all. What that says is that there was a dense carbon dioxide in the atmosphere in the past. The CO2 went someplace else. It didn't go into rocks on the surface because you had this acid environment on the surface and you couldn't precipitate carbonates.
And that acid environment is in the form of, well, sulfuric acid.
Sulfuric acid, yeah. What happens is when you have water that is present in a volcanic environment, you can get sulfuric acid form. There are places on Earth where you have acid lakes and acid rivers, and interestingly, despite the fact that you can get very low pH, very acidic conditions, these things tend to be teeming with life. It's just life that has managed to adapt to that very acid environment.
So what does that tell us about our chances of life on Mars?
That's a good question. Because it was acid, it might have made it very challenging to possible Martian life. The thing you have to realize, if you take a look at one of these little acidophile bugs that's in this acid water, even though they might be living in a bath that's pH 1 or 2, very, very acid, if you measure what's inside their cell membranes, the chemistry is neutral. And they managed to actually preserve neutral chemistry inside. So that says that they probably were not originally created in that environment. And whether you can actually get the chemical reactions that lead to the origin of life to work under very low pH, under very acid conditions, is an open question. It may be tough.
And a question for future missions.
A question for future missions, yeah, very much so.
Originally the Glamour rover, Opportunity has had its fair share of ups and downs in the past 3 years. After exploring Endurance Crater, home to more sensational outcrops, it spotted a distant target and headed off across the sand dunes. All was going well until a wheel slipped and became stuck. Back on Earth, the mission team battled with a replica of the rover to plan an escape. Eventually, after 38 long sols, the rover was free of what became known as Purgatory Dune. By September 2006, Opportunity had reached its brave new world, Victoria Crater.
We spotted Victoria as a target the night that we landed. There was this monstrous crater, 800 meters in diameter. We had no idea how deep it was. It turns out it's like 75 meters deep. And I remember the night we landed joking about, boy, wouldn't it have been cool if we had landed there instead? Never thinking that we'd have a chance to drive that far. But after 21 months of struggling across the dunes and the drifts, we finally arrived at the rim of Victoria Crater, and the place is just spectacular.
And what sticks in my mind is this incredible image of Opportunity from above.
Ah, yes. Well, that was very special. This marvelous camera called HiRISE on the Mars Reconnaissance Orbiter spacecraft was turned on and operated really for just about the first time at Mars. The resolution of that camera is phenomenal. It's about 30 centimeters per pixel. So you could see the rover.
And you can see the rover tracks.
You can see the rover tracks. You can see the rover itself. You can see the high gain antenna on the rover deck. It's just phenomenal. And that image, it's hard to describe. My reaction when I saw it was so good to see the rover again.
So do we get to go into Victoria Crater?
I hope so. I really, really want to go into it. The beautiful thing about Victoria Crater, well, there are two things. First of all, it's much deeper than Endurance, so we see an even bigger slice of Martian geologic time.
That's further back into time.
Further back into time. But the other thing, and this may actually turn out to be more significant, is that the one thing we couldn't do at Endurance was see how the geology varies laterally. We were able to see how it varies vertically because we went down into the crater. But the Endurance crater was not that big.
So you only have 1 point.
Essentially, you've got this one vertical slice through the crust. What we've got with these promontories that are dotted along the rim of Victoria Crater is we have literally a couple of dozen vertical slices through the crust, and they're spaced 50, 100 meters apart. We go to one, and the next, and the next, and the next, and it's like it's as if you could go and drill a series of boreholes, you know, and we can look at every one of them, and we can look at both the vertical changes in the geology and the horizontal changes in the geology, and that's going to be really different from anything we've done before. At Endurance Crater, we made a decision that we weren't going to go in unless we could definitely get out again, or at least feel pretty confident. Victoria is a more difficult crater. It looks steeper, it looks more difficult. I'm not sure if we go in whether or not we can find a safe way out. But if you ask yourself, where's opportunity going to go next? There's nothing. I mean, there's nothing for miles in every direction. So this is the best science target we've got. I think even if we can't get out, going in may be the right thing to do.
It's a big place to play around.
It's a big place to play around, and we could spend months, probably years, exploring this crater. But if we don't have to do a suicide dive, I'd rather not.
The Martian winter is harsh, with temperatures dropping far below minus 100 degrees Celsius. The rovers have just enough sunlight to keep their solar-powered batteries charged until spring. Having now survived their second winter, the rovers will soon be up and continuing their adventures. Eventually, they should have company in the shape of Bridget, Europe's ExoMars rover, which hopes to launch in 2013. One of its designers, Lester Waugh, met Steve to exchange ideas. Well, Steve, meet Bridget.
Yeah,
this
fabulous.
Is the European, and Lester, the designer. What do you make of it?
It's wonderful. It's very similar to our vehicle in some respects. Six-wheel drive, four-wheel steering. It's got a suspension system that can go over different kinds of rocks, but it's designed differently. It looks like a terrific vehicle. I noticed the arm in particular on the front of the vehicle is very similar. Ours, 5 degrees of freedom, right, with a shoulder and an elbow and a wrist.
That's right.
Very similar to ours.
This is actually an engineering model from Beagle. As you say, it is a 6-wheel drive, 4-wheel steering. The wheels that we have are slightly different to yours, and that what we've tried to do to reduce mass is to have a flexible rim rather than flexible spokes, which is effectively what you had.
It's really important to keep the mass down, isn't it? That's the biggest challenge.
No, it's one of the biggest challenges. There are a whole bunch of other ones, as I'm sure you know.
There are. One of the reasons also that we don't have 6-wheel steering, which would be very nice, is to try and keep the mass down as well. This is something that we're currently trading off, and it's something that we have to consider.
I'm a big fan of 6-wheel steering. I've used both 4- and 6-wheel steering on rovers, and having that ability to drive the whole vehicle sideways can be extremely useful when you're trying to work in difficult terrain. Plus, it's great for parallel parking.
Yes, sure.
Spirit and Opportunity were the first probes to release images direct onto the web. Well, NASA really hasn't got time to examine all these closely. Others have. And Mars enthusiasts over here have been doing just that. I talked to one of them, Doug Ellison.
Each rover is equipped with 9 different cameras, but the most important 4 are the ones atop of this mast here, and they're called PanCam and NavCam. Now these are just a few of the frames as they appear straight onto the internet, and they're uncalibrated. So 2 frames beside one another won't match up particularly well. They're stretched so that everybody can see something. With a lot of careful work and a lot of careful processing and a lot of practice as well, enthusiasts can produce a colour image.
I mean, if you're on Mars, would it look like that?
I think it's fair to say that from an artistic perspective, perhaps, that is a fairly true rendition of what Mars might look like to a human sat on the surface.
What kind of interesting things you found out so far from these pictures?
I think one thing that amateurs have done that was particularly incredible is that it's a very rapid turnaround. Because there are so many amateurs looking at so many pictures, nothing can happen on Mars without us spotting it.
No.
And that includes things like dust devils, or in the case of Spirit, where it's been sat in the same place for just over 6 months, the amateurs have spotted changes in the surrounding terrain, which we're assuming is dust devils.
So Mars is certainly active.
It's certainly not as dead as people would have you believe.
Doug, thank you very much.
Thank you.
Over the years, there have been many missions to Mars. Some have failed, others have succeeded. And recently, NASA has had great success. Chris went over to the Jet Propulsion Laboratory to find out more about them.
I'm at what for over 70 years has been at the heart of the US space exploration program, the Jet Propulsion Laboratory in Pasadena, California. Recently, much of the effort's been focused on Mars, with a whole string of successful missions planned and then controlled here at JPL's leafy campus. There are 4 modern spacecraft orbiting Mars, 3 from NASA and 1 European. All build on the success of the Viking missions, which had both orbiters and landers. When they were launched in the mid-1970s, these were the most advanced and the largest spacecraft ever to leave the Earth's neighbourhood. Viking's goals were bold: to follow hints from orbit that Mars once had water by looking for the signs of life directly. NASA's strategy was to follow the water, an idea which was to influence all later missions. The thought was that where there is water, the chance for life may exist.
Well, at the time of Viking, we'd seen on the surface evidence that there were ancient floods, possibly rivers flowing over the surface, but this evidence was entirely morphological. We only had a sense that, in fact, we were looking at a planet which long ago had water on the surface. But we felt at that time bold enough for the Viking mission to actually land at 2 places and search for life.
What did we know after the missions? What did the Vikings tell us?
Well, with Viking, the science community attempted what I like to call a scientific home run. We attempted at that time to actually in a real sense, to find life on another body and to evaluate the organic molecules all the way through to very complex organisms. And we found nothing. We found the planet to be extremely sterile, so sterile in fact that it remains a surprise to us. The mechanisms are still somewhat mysterious as to how the planet has become so free of organics. As we looked at that result, NASA and the public all kind of imagined that we were spending time on a planet that was dead. It was no longer interesting. And so NASA moved on to the outer planets, and Europe with it.
And there was a gap of, some 20 years before the next missions to Mars. Why did we suddenly go back?
Large numbers, hundreds of scientists were still mulling over the Viking results 20 years later. And it was the sense that new data was needed in order to put an end to some of the questions. And water was one of those. And so the groundswell developed into what I've described as the Mars Observer, which had a fatal ending prior to taking any measurements, but it was really, if you like, the first step to our return after 20 years.
And then Global Surveyor came and was a great success.
It was. It was a terrific mission. All of us breathed such a sigh of relief that the engineering worked and that the science was finally producing data. One thing that we found was that the evidence for water was very great. There were such diverse characteristics on the surface of various parts of the planet. And we began to ask the questions, well, if we were going to look for life, does the MGS data tell us where to go?
In its 10-year mission, Mars Global Surveyor was able to image the same parts of the planet many times. It managed to detect changes on the surface, like this brand new impact crater. More importantly, gullies like these seem to have been filled with fresh deposits of bright material, suggesting that liquid still flows, albeit occasionally, on the surface.
The conditions on Mars do not allow for water, liquid water, in equilibrium with the atmosphere. So how do you get the flow of water? And there's a variety of ideas. The two that are competing now are groundwater, perhaps behind a stopper of ice, where groundwater a few hundred meters below the surface is seeping out as the sun warms the ice plug. And the other is, in fact, that this water flow occurs beneath snow, ice that forms, water ice that forms on the surface, and as it begins to sublime into the atmosphere, there's just brief periods where water can flow underneath. We right now don't have the measurements that will tell us one way or the other.
But those are both fairly familiar Earth processes as
Yes.
well, so we can use our intuition and try and distinguish.
Well, in fact, intuition based on Earth experience is an old bugaboo of planetary science. we tend, because that's our experience base, to say, well, I saw that out there in the desert and, you know, maybe this is it on Mars. But as we explore Mars more and more, we see the limitations of those Earth analogs. But we have no choice for processes that we can't actually observe to reflect upon what we see on Earth through field studies.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying NASA on an odyssey back to Mars.
To help build up a better picture of Mars, 2 missions have followed Global Surveyor. Odyssey in 2001 looked for water in the polar regions. And just last year, Mars Reconnaissance Orbiter, with its amazing camera called HiRISE, arrived at Mars.
Here's an area here that is about maybe 1 kilometer wide. We're really zoomed in close. Our full image is about 6 kilometers wide.
So how big is the smallest feature that you can see on a HiRISE image?
Okay, the pixel is about a foot square, about like this, 25 to 30 centimeters. And to really see a feature well and know that it's a boulder or a crater, you need about 3 pixels. So we like to say it's about meter scale resolution.
So we could see this table?
Oh, yeah, very well.
And you've been in science orbit now. It's coming up to December, so just under a month. And what are the highlights so far?
Oh my goodness, there have been so many of them. We're seeing Mars for the first time. What a lot of the public really likes seeing is our debris on Mars, the past landers and the parachutes. And we've also recently imaged both Viking landers 1 and 2.
And here we are. This is Viking 1. It's still on the surface after, what, 30 years?
Well, it hasn't gone anywhere. It doesn't really have anywhere to go. Here is one that we just got today.
Oh, wow.
This is a crater called Odomon, but we're zoomed out by a factor of 6 here.
Mm-hmm.
But what's interesting in this location is that here's the central peak of the crater. You can't quite tell that's what it is. The crater is bigger than the whole image.
Mm-hmm.
But what we've seen are that these layers appear to be standing on end. So we have layered rock on Mars. Here's a place where the impact crater, the central peak, has turned the whole section on its side. So now we can look straight down on the stratigraphic section.
So these little dots that we can see are a couple of feet across. These are boulders, I
Yeah,
guess.
the boulders there are at most a meter diameter, so, you know, close to the size of a person.
And what's causing all of this cracking on the surface?
Okay, so what happened here is that there were a sequence of layered rocks from sediments, from maybe streams, maybe aeolian, whatever. Mm-hmm. Then the impact happened, and the central peak of the impact, of large impacts, gets uplifted. So you get the deep rock lifted up, and sometimes it gets turned over as well. That's apparently happened here.
Well, Chris was telling us about the NASA probes. But I'm glad to say we have our own European probe, Mars Express, now going around the red planet. And I'm joined now by 2 experts, Professor Jan Peter Muller of University College London and Dr. John Murray of York University. Welcome to the Sky at Night. Peter, may I come first to you? Can you give us a general rundown on Mars Express?
Mars Express has been circling around the red planet for just over 3 years now. The spacecraft has 6 instruments on board, and we're involved in one of those instruments.
So let's have a more detailed look at some of these marvellous pictures.
So what we're looking at here is a 3D animation which has been created from stereo pictures taken from above from the Mars Express spacecraft. This area, called Iani Valis, looks like a huge channel which has been scoured out by water at some point in the last 15 million years.
Did you expect this kind of thing, John?
The interesting thing about these events that we found on Mars Express is that they're so much younger, and they're very, very large water eruptions we were talking about, catastrophic events, very, very much bigger than anything we see on the Earth. There is really no equivalent for this kind of thing on the Earth. And it's carved out these vast channels which are tens of kilometres wide, and they go on for hundreds of kilometres. But in the relatively recent past, and we're talking about 5 tens of millions of years rather than thousands of millions of years, and that is a great surprise.
Well, there are plenty of surprises. What about the question of ice at the equator?
Yes, that's right, yes. We found a very large frozen sea near the equator of Mars. It's about 50 metres deep, something like that, but extends over several hundred kilometres. It's covered with dust, so that protects it from subliming away in the thin Martian atmosphere. Now, this frozen sea seems to have erupted from a series of cracks known as the Cerberus fossae, which are 200 or 300 kilometers away. And they seem to have cracked right down to the liquid water beneath the surface, huge reserves of liquid water. You've had a very large eruption of water that's flown across the surface, carved out a large valley, the Athabasca Vallis, and then spread out and ponded in the low-lying Elysium region of Mars. Now, the exciting thing is that this appears to have happened very recently in geological terms, something like 5 million years ago, a long time to you and me, but in geological terms, it's just like yesterday. So the implication is that this sort of thing has been happening throughout Mars' history and could happen again in the future.
One rather bizarre touch. Peter, what about the Martian face that was first shown by the Vikings?
Yes, it was first seen by the Viking spacecraft, and much interest has been generated by this face all over the world. These pictures taken last summer have been converted into 3D measurements and animation created. And here what we're seeing is the so-called face of Mars. A little difficult to recognise the face, however.
No Martian civilization, I fear.
They'd have to be underground.
Peter, John, thank you very much. Well, those are our current missions, but what about the future? NASA has some great plans ahead. One of these is Project Phoenix, and Chris went over to Tucson, Arizona to find out the latest news.
Launch is due in August, and work is underway to turn this into mission control, ready for the team once Phoenix touches down near the North Pole in May 2008. This area is gradually being transformed into a replica of the landing site, and the model behind me has the same set of instruments as will fly on the real thing. This simulated environment allows the mission team to test how the lander will behave and to train the scientists that will use it for real.
We only have 3 months on the surface to do all the science we need to do to meet our mission goals, so we don't want to be kind of fumbling around and trying to learn how to drive the spacecraft when we're actually there. We want to have a trained team that knows exactly what to do, given any of many different possible types of terrain to deal with.
Phoenix has got a very specific job to do. There's one mission in mind, so what is that?
The job is to verify that the Odyssey discovery of ice in the northern polar plains is real, how that ice is layered into the surface and interacts with the atmosphere, and what's the history of that ice? I mean, how did it get there? Did it come from the atmosphere? Was it the remnants of an ancient ocean? Did the polar cap used to be there?
The Mars Phoenix mission has a new landing procedure using both parachutes and rockets. The exact landing site is still to be determined, but will be in an area where there are polygons, features which, on Earth at least, mark ice lying under the surface.
What we see is polygons within polygons within polygons, and the polygons are basically cracked soil that cracks in a polygonal pattern, and as the ice expands and contracts, it doesn't necessarily have to melt, but it expands and contracts with temperature, and as it contracts, cracks form, and sand can get into the cracks. So when it expands back again, it can't go back to where it was, and it kind of corrugates the surface in a funny way. This is very similar to terrain we see in the polar regions on the Earth, so it's not unusual to have these kind of shapes with ice near the surface. And that's exactly where we want to go. In fact, the polygons go down to such a scale that we're hopeful now that we'll be able to actually dig in various types of terrain that are pushed around by the polygonal structures, maybe in a crevice and then on a mound next to it, and we can look at the differences.
For Phoenix, there's a very definite end to the mission, isn't there?
There certainly is. We're inside the Arctic Circle on Mars, and when the sun sets, it gets dark. Our solar panels produce no energy, and not only that, on Mars, the atmosphere actually freezes out to the surface. We're going to be encased in dry ice, carbon dioxide ice.
The next NASA rover is the futuristic Mars Science Laboratory, due to get to Mars in 2010. Because of its size, the rover will be gently lowered from a hovering platform, known as a sky crane. It's an incredibly ambitious landing. Its aim is to find out whether the hostile environment of Mars can in fact support life. With its advanced suite of instruments, it will vaporize rocks, analyze samples, measure radiation levels, and monitor the climate.
The primary intellectual focus is on habitability. Could Mars sustain life? Based on what we know that we think we know that there was water, we know things about the climate, we know some things about the rocks, but can you actually get in there and figure out, by comparison to what we know on Earth about where life can thrive or exist, is it habitable?
So do you believe there's life on Mars?
Life on Earth is capable of living almost everywhere. Even reactors. Nuclear reactors, apparently there are bacteria that can live in the walls of nuclear reactors.
But what we don't know is how likely is it gets started.
And there are some people think it's very easy to get started, and maybe once it gets started, it's hard to keep it out of everything. People want there to be life. But when you ask, do I believe, I have no basis for it. It's a sociological phenomenon that the extrapolation from the extraordinary capacity of life on Earth to go almost anywhere, to invent new metabolisms to deal with whatever nutrients happen to be available, has gotten generalized to, if it could exist someplace, it does. I doubt it's true, but it is the popular opinion. But it's an excellent question, and you should come back in 20 years and evaluate how sociologically the scientific community and the world at large has come to think about where and how life can exist in the solar system.
Beyond Mars Science Laboratory, there's a big change in NASA's philosophy. After follow the water, it's find the methane.
Well, our plan is to follow up MSL with a mission in about 2013 that we call, again, the Mars Science Orbiter this time. And its purpose is to follow up on some really exciting results from Mars Express. In fact, one of the exciting results out of that mission is the detection of methane in the atmosphere. Maybe follow the water, which we've been doing, isn't the only way of searching for that pot of gold, the evidence of life, for two reasons. First of all, organisms, even very rudimentary organisms, can produce methane. The second possibility is it's not life at all, it's a geologic process. Well, that's interesting too, because if you were going to look on a planet for living organisms, you'd want to go to the warm environments. And methane can be produced geologically, and it's quite happy if there's water present. And so the way in which we're thinking is that if we could find sources of methane on the surface, whether they be organic or not, you'd want to follow those. And so the future missions of landers and rovers might go to the sites that this Mars Science Orbiter discovers.
For NASA, plans for sample return and for manned exploration are still decades away. Still, the idea that Mars is a dead world has long gone, and instead it seems to be a planet filled with hidden promise. Exploration of the red planet is sure to continue to amaze and astound us.
As you can see, our views about Mars have altered beyond all recognition over the last few years. And I wonder what lies ahead. Above all, is there any living thing on Mars? I don't yet know. Perhaps in the fairly near future, on the Sky Night programme, we may be able to tell you.